Okay, let's start right now. Okay,ครับ. If you recall from the very first lecture, we set the scope for this class. Okay, the scope of the class is that you want to study big data, right? The big data in our oh good. Oh good, we can now really start. Big data and analytics. Okay. That's the objective of this course, all right? Big data analytics. We've decided that from our perspective, big data, okay, two things has to be the key element of what it means to be big data. It's the fact that it has, variety, velocity, volume, and all that. Okay? Because of the volume thing, and also because of the velocity, okay, because of the volume and the velocity, it requires the second element of big data, which is the technology, okay? So the like computation platform. Okay? And we said that's where the Hadoop, this MapReduce, all this thing, which you really cannot learn in class. Okay? Which you cannot learn in class. So this is about distributed data storage and distributed processing. So starting with the MapReduce paradigm, it's spun up into Hadoop, distributed data system, and so forth. This is something that you cannot really study in class, and you don't really have a lab here. Okay? You don't have a Spark Station lab type thing to simulate. So what we can do is we can focus on this bit, which is data analytics, right? Tools to analyze data. Okay, tools to analyze data. Okay. Now, if the data is sort of like traditional, okay, and you work with things like distribution, you can do statistics. And that's your year one, right? But if you want to do some kind of learning, machine learning, okay, then this is where we focus a lot of our project work. Okay, this is the bulk of our data. Okay, so let me summarize again. Big data and analytics. The big data implies that the data itself, okay, the data itself is big, volume, okay? It comes at you hard and fast, velocity. And it comes in many forms. It's not just numerical, it's text, it's picture, it's audio, it's video. So it has variety, okay? But really, it's because of the velocity and the volume that requires a very large parallel computational platform, okay? And that, again, start off with the MapReduce framework that has been since implemented in Hadoop, in Spark, and all kinds of commercial platforms. This is something you can't really learn in class. You have to have a lab, okay? So we'll focus on the data analytics, tools to analyze data. Now, tools to analyze data, if it's in the form of numerical data and you want to know what the distribution is, you already had that tools in your year one. Okay? That's statistical tool. Okay? That's statistical tools, right? You had that in year one. But if you want to analyze in terms of relationship, okay? If you want to analyze in terms of relationship, like how are data clustered together, how can we predict Y from X, okay, in a non-linear way, okay, then you have to go to machine learning, and that's the bulk of our class, Now, today, I'm going to recall the third definition of big data, which is the variety part. Okay, variety part, right? The variety part means you don't just have to deal, you can deal with not just numerical data, but you can deal with all kinds of data. Okay, so this is a variety thing. Now, you have to deal with a variety of data to map into your machine learning problem. Okay, that's what we are doing. In fact, one of the projects, the discoloration, where's the discoloration project? Where's a defect, okay? It's one of those where the data is not any numerical number, but it's actually spectral scan of the picture. So it's picture into spectral scan and into some kind of input to machine learning. Okay. Today and next lecture, okay, I would give you other things over here. In other words, more variety of data that you can play with. What I might do is make a diagram summary of this, but it's actually in the mind map. Okay, all of this is in the mind map. I'm just citing part of it. Okay, so this variety, okay, audio data, we're not going to deal with that in class, not too much. Okay, so we won't talk about it. Not that we cannot do. We can. We can do chemical analysis. You can literally use machine learning that feed off of aromatic sensor. Okay, I may have mentioned that when I long time ago, even when I was a student, there was an effort to connect wine, okay, that has a scent, and there's a chemical sensor, okay, and this feeds into a neural network and try to identify what wine variety that is. Okay, so in this case, that's an early example of this kind of big data thing. Okay, so chemical signature, chemical information. I don't know what that is. Okay, I mentioned to you that I was giving a talk to bioinformatics lab. So bioinformatics, in particular, information about genetic, okay, or genomics. Genomics. By the way, there's another word called transcriptomic, but you don't understand it yet. But basically, it's about gene expression, all right? So you can use it as input, all right? And output could be something, you know. In this case, input could be genomic information. Output could be something like vulnerability to cancer. Yeah, something like that, okay? You can also do genomic study on the cancer cell, not just on healthy cells, right? You can do video. Yeah, we're not going to do that in class. It's too difficult. We can do visual or picture. Yes, we're going to do this one because that's also part of the project, right? So chemical information, no. Bioinformatics, no. Picture, yes. Yeah. Of course, if it's numerical, then it's obvious. A lot of projects are based on that. So visual picture, yeah, yes. What else? Words. Yes, we're going to talk a little bit about that. And I think one project is making it more relevant. I was kind of hesitant about, you know, when or where to cover this thing. Yeah? It's a big area on its own. Okay? I don't get very much into it personally in my work, but certainly it's becoming more and more important. And I'm glad that at least one of the project has made this more important, at least for this class. Okay, so visual or picture, words. Okay, what else? What else are we gonna look at? Well, today we're gonna talk about this thing called graph. Okay, so today graph, maybe next week words. Yeah, graph and words. What are graphs? What are graphs? When I tell you that we're going to talk about graph as an input, what do you guys think of? Well, normally when you think of graph, this is what you mean, right? Some kind of chart, some kind of plot. Well, this I would call chart or plot. Yeah, when you have something like X and then you have Y and then you have something like that. I don't call this graph. Yeah, look at me. This is not a graph. Okay, from now on, you're a data scientist. You call this a chart or a plot. You will not call this a graph ever. Okay, you're no longer allowed to call this a graph. Okay, what is a graph? A graph is a mathematical object. Just like number is a mathematical object. A graph is a collection of nodes. Yeah, this guy is a node A. This guy is a node. Yeah. And this is a connection between nodes. Okay, it's called an edge. Okay, it's called an edge. Now, you have two choices. You can call another name for node. It's called vertex. Okay? Or many of them you call vertices. Vertex. And instead of calling edge, you can call it arc. Okay? So, a graph is a collection of two things. Edges and node, or node and edge. Let's start with node. Okay, or vertex and arc. Okay, now this is what a graph is. But notice the edges are not just any line. They have to connect between arcs, right? In other words, if I call this collection of city, right? I put city in singular because it's a single noun, right? But all of this is city, okay? And a collection of highway. Can I do that? So this is all the highway systems, right? What's important is that the highway is not just built randomly. It has to be connecting from city to city. Okay? Has to be cities from cities. Okay? So this is intercity highways. Okay? Okay? So imagine that this is a graph. Well, not imagine. This is the definition of a graph. A graph is collection of nodes and edges connecting them, or you can say a graph is a collection of vertices with arcs connecting them. Okay? Now, so let me put here as the variety, i.e. not numerical vector. Okay, we're gonna do picture, we're gonna do graph, and we're gonna do words. Okay, picture we have done to an extent last week with the example of the convolutional. We're gonna do graph today, and we're gonna do word next week. Okay. And again, this is what's the team that's switching to the word-based project? What's the name of the team? Team Lai Luk. The word team. There's a team that's switching to the words. Team Lai. No shield. No shield. Okay, that's good. I'm glad. Okay. Graph. I think picture. I think we have the Wang. Okay, and quite a few over here on the numerical thing. Okay. Right. So we are going to talk about graph object. Now, first of all, without going to the slides, okay, I'm actually going to give you some of the presentation slides. Without going into that, can you guys think of what is a graph in your life, let's say? What's an example of a graph? Bus stop is very good. Bus stop, okay? So bus stop would be example of nodes, right? So this would be something like stops, and this would be some kind of route, right? Right? Okay? So actually you can have 2 bus stops connected by 3 different routes. Maybe the route is unique, maybe not. Maybe one goes this way, one goes the other way, one takes a scenic route and so forth, right? What else? I'm looking for something that's more your generation than mine. Social network, right? Social network. Now, network is a word sometimes substituted for graph. Okay? But network is a general term. It's not a mathematically precise definition. So a network, which just means that things are connected. You can talk about social network. Now, by the way, before Facebook, when we talk about social network, you know what we meant? In the scientific community, we meant the social network. We literally mean society. In some countries, like in the, say, in the Western culture, when people get old, okay, when people get old, they become vulnerable because they don't have the social network. When we say that they don't have a social network, we mean they don't have a support structure. In other words, if their children don't take care of them, they die alone. That sort of thing. In Thailand, let's say you're a grandmother, and maybe the children have gone to work in the big cities or whatever, you still have neighbors taking care of you, that sort of thing. That's what we mean by network. Okay? That is the earlier definition of social network. It's a sort of support structure that comes from a society. Okay? So in the Western country, if you're old and the children don't come and visit you, nobody else does. Okay? But say in Thailand, if you're old and your children are working in the big city somewhere, you still have neighbors and cousins and so forth. That's called social network in the earlier definition. But now, with Facebook and Twitter and whatnot, okay, social network, this means connection on electronic platform. Okay? First of all, what makes it social? What makes it social? What makes it social is because it's completely a social phenomenon. You are connected not because you have to be connected. Now, when I say, okay, everybody who's taking this class must sign up for a line, okay, that in a way is not social network because I'm making it happen, right? It's a structure, it's a class assignment, right? Everybody has to be on the group line so I can give you guys assignment. Okay? Well, social network, when you have your line group, it doesn't happen that way, right? You organize, say, maybe you are in a table tennis club or something like that. You connect 5 people, you add more friends from the real tennis club, or add more friends from the chess club, and so forth. And it just grows and grows. It's a social phenomena thing. That's what makes it social in that sense. Okay? What makes it a network? The network part is the graph part. Okay? It's the graph part. It's the connectedness. Okay? But from now on, this kind of, I'm going to say network is a general term for interconnectedness. Yeah? Network is a general term for interconnectedness. I'm not going, some people will say network data, but from now on, you guys are going to use the proper term, which is the graph data. Okay? So graph is precise. Graph is precise. It literally tells you how many nodes you have, how many arcs you have, and how are they connected. Precise. It's not loose. It's not like, oh, you know, don't worry about this guy because he, you know, even though he loses his job, he has social support, social network. That's not what we mean. So a graph is precise. Okay? But the network is a general concept of how things are connected. Yeah? You've seen this word before with neural network. It's the connectedness among neurons, right? Artificial neuron. That's why you make it neural network, network of neuron. But mathematically, it is a graph. Yeah, so that's it. That's the definition of graph. And I'm going to make an assumption that you guys are familiar with the social network concept enough to understand what it means. Okay, so when you say social network, if you think about it, to write down social network, you have to store it. Think of graph as a database for storing social connectedness. Okay, you can think of it that way. Some people do. Okay, that's why there is this thing called like Neo4j, which is kind of like a graph database. Some of you might be familiar with, but it's very interesting. So that's what a graph is. That's what a graph is. Okay. Now, so oops. Okay. So I'm just going to run through, and these are kind of prepared slides. So I'll run through some of them in various speed. Sometimes quicker, sometimes I would stop and pause. Okay. So we are in a network-centric, okay, society. Okay. So the network, it's not just not just you being on a network of the line group and Facebook and so forth. Everything, supply chain is a network. So there's a lot of phenomena in your life. It has to be with social life. It has to be with economic, supply, material flow, how gas flow from natural gas mining all the way to your car. That requires some kind of pipe. Pipe goes from place to place, right? Right? So you can imagine that pipeline is also a network. So we can talk for hours about what in your life can be understood as network, as graph. Okay? So suffice it to say that what's happening is we are surrounded by graph-like phenomenon. Everything in our lives, okay, is organized as a graph, or can be conceptualized as a graph, as an interconnectedness among entities. Now, the second thing you have to realize, there's this thing called emergent properties. Okay, this is a very modern word. Well, it's not that modern anymore, but it's a word that you have to operate with. Emergent property can be thought of as a scientific way of saying that there is more to the whole than the sum of its part. Okay, that's what emergent property is. Okay, or there's more to the dynamics than can be predicted. So if I say something like, you're good in math, say you're good in science, you're good in science and art. Okay, I put you together, 5 of you, and emergent property could be something like, this group is also excellent at philosophy. Okay? It's something that you cannot account for by individual pieces. Okay? Now, individual pieces like this is easy to conceptualize, but there are other things that are more difficult to conceptualize, like rule. Let me give you an example. A simple rule is like this. You are a fish. Okay, here's a rule. You are a fish. You turn right when the fish to the right turns right. Okay, that's it. That's it. It doesn't say anything about turning left. It doesn't say anything about going straight. You just do whatever you want. You just add this rule. Just add this rule, okay? You look to your right. Whenever the fish to the right turns right, you turn right. Some simple rule like that, okay? Very simple rule. It turns out that when you implement certain simple rules like this, you can get a whole school of fish to coordinate their movement. That's also called emergent property. Okay? Emergent property. Now, the emergent property that we're talking about, and emergent property is part of what's happening in your life because of whatever it is. Sometimes unintended consequences happen. Sometimes some kind of natural organization arise out of chaos. You just have fish that follows a simple rule. Now, the basic thing, the most obvious, I'll just give you a side thing. It's called automata. Yeah? Go search this thing in maybe internet or something. Automata. A-U-T-O-M. Cellular automata. Yeah? If you have a lot of time, I'll show you this, but basically, you just have cells of things and have a simple rule like if the right is black, I turn black. If the right is the left is white, I say do nothing. Okay, and after a while, it creates a pattern. That's called emergent property. Okay? So, 2 things. You are surrounded by network or interconnectedness of things, of yourself, of energy, of supply chain, of food, information, of everything. It's all interconnected. 2, out of this interconnectedness, sometimes there arises emergent property that you cannot predict. You cannot predict just by looking at individual connection what's going to happen. Okay? It's like you cannot predict the swarm of bees movement just by looking at 2 pairs of bees. Okay? Just pairs of bees, how they interact. If you look at them, you can't guess what's going to happen to the whole swarm. Okay? So that's why emerges this thing called graph data and graph learning. You're trying to learn the behavior of the emergent property. Okay? Now, so right? So we're going to talk about the graph, what do they look like, and how they can be captured as data or as input variable, so you can analyze. Okay, hold on, where are we? Oops. Okay, we are going to study this thing called centrality. Yeah, so the emergent property that we talk about can be many things. It can be something like sensitivity or collapse, or it has many things, like movement in fish, right? So we're just going to focus on one emergent property. Yeah, one emergent property, which is called centrality. Yeah, centrality. Now, let's make a little experiment. Well, not experiment. All of you are equal. All of you are equal, right? You're all students. You're all students. Now, let's say that you can know the phone number of one person in this room. Okay? Let's make an experiment. Okay? There are 20 of you. Okay? I'm just going to draw 6. There are 20 of you. Okay? Each one of you can only know the phone number of one person. Okay? Fair enough. Still equal, right? Everybody knows one. Nobody has an advantage. Everybody knows one number. Okay? Or you have one line connection with one person. Okay, let's make it line connection. Now, imagine this. That this is the line connection. This is the line connection. Yeah? If it's like this, everything is symmetric. You can talk to you can talk to him, you can talk to this person, blah, 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 right? There's no emergent property because, well, you started out even, you're still even. Imagine if I organize it differently. What if everyone, still one connection is, right? But it's to this guy. Look at me. Look at the board, guys. What's happened? Okay. Now, if I look at each pair, it's innocent, right? I can't tell what's happening. It's just two people talking. I look at another pair, it's just two people talking. But when I look at the whole system, what emerges? What emerges from this? What emerges is that this guy is the plays the central role in this, right? In other words, the entire communication shuts off if his phone goes dead, right? That's the emergent property. It's the centrality. It didn't happen before, right? And I can't tell by looking at individual components. Okay? But by connecting it this way, this is the emergent. Emergent is the centrality of one guy. Now, this is a little bit extreme, right? This is a little bit extreme. Again, two situations. There's this one, and there's this one. Okay? Again, we don't have a line group, we just have pairwise lines. And I want to say, I'm going to tell all of you about what's going to be on the exam, or what we have to study. What network do you prefer? Yeah. If there are 20 of you, and one of you, the phone fell out, just dead, the battery is dead. Okay? Then you lose that one person. Same here. But for this graph, any one person can be lost in the communication. In this case, if this guy goes to sleep or doesn't turn off on his telephone, his phone, his line group, he doesn't read his line, nobody gets the message. Okay? This is an emergent property. Okay? We'll call it centrality. Now, the flip side of centrality sounds good, right? Sounds like this guy is central, so he's like the big deal. So sounds good. But what it also means is the network is fragile. Okay? So he is important. This guy is important, but not because he's a nice guy or whatever. but he's important because systemically, he is the weakest link. He's the weakest link. Okay, because the weakest link in this case doesn't mean that you are not pulling away. It means that if this guy fails, everything fails. That's what weakest link means. Okay. So, okay, again, I keep repeating the concept so you understand. We're studying big data. The part that has to do with computational platform you can't study. So we focus on analysis. The analysis, we can't deal with big volume or big velocity, but we can deal with variety. And the variety that you have started to deal with is picture. And there are two more that's going to become relevant. The other one is the word data, and the other one is the graph data. Today we're talking graph data. So, graph, again, why is it relevant? So it's relevant for two steps, by the way, two steps. Step one, the world is organized as a graph. Step two, when there's a graph, you can get emergent property that you didn't have before. Okay? We saw that right now. Okay? This emergent property we call centrality. There are other emergent properties that come with graph, that comes with school of fish swimming together, and so forth. But we don't care. Yeah, we're just going to talk about this because this is relevant to data analysis. Remember, I have a job to edit what I teach you. So machine learning, for example, has 3 paradigms. I'm going to teach you just 2 because the other one are not so much relevant to data analysis. It's relevant to robotics, say. Okay? So likewise, there are emergent property of systems. You can get a whole, 20, 30, 40 PhD thesis on emergent property of graph or something like that, right? But the only emergent property we are interested in is centrality. Now, we are not interested in just existence of centrality. In other words, is there like one person who is the weakest link? We also want to identify who he is, right? In this graph that we showed before, where one person knows has a high connection with one more person in this room. There's only one person that has to make sure the battery is really never goes down. So, from a societal point of view, I have some amount of money to buy extra battery. Who am I going to give it to? That one person, right? Because that one person, I don't really care about him, really, right? It's not that special to me. But if he goes down, nobody gets the message. So I'm going to give a preferential treatment for that reason alone. Okay? Right. Now, the discussion today here is that going to be about graph theoretic properties called centrality analysis. Okay? And there are many emergent properties. One of them is a class called centrality. But centrality is not uniquely defined. Okay? Let me show you what it means. There are many different definitions of centrality. For this class, I'll talk about degree centrality. I'll talk about closeness centrality. I'll talk about betweenness centrality. And I'll talk about eigenvector centrality. Okay? I'll focus a lot more on eigenvector centrality. My own research actually extends centrality, eigenvector centrality. We'll talk about that. But eigenvector centrality actually was due to Bonacci in 1987. That was the breakthrough, I guess. Okay. Now, this I want you to see the historical root, right? In the old days, right? In the old days, well, not in the old days, even right now. Okay, there's a city called Königsberg. Anybody been to Königsberg? Well, anyway, doesn't matter. The city looks like this. This is from like, I don't know, 300 years ago drawing, okay? You have little island and little edges, and you have bridges. You have bridges, okay? You have bridges. And the puzzle was, can you find a tour? Can you find a tour that crosses each bridge once? Okay? So you can't go back. You can't come back and repeat, right? Just once. You have to traverse once. Okay? This problem was not solved because it's a puzzle, right? People have tried different ways and so forth. It turns out that if you turn, okay, if you turn island into nodes, bridges into edges, or vertices and arcs, then you get the top left graph. See that? A little bit small. And you can count the number of edges and number of connections, and you have certain property you can prove whether or not this is doable. Okay? Hence, it has to do with something like the number of edges versus number of arcs. Like if you don't repeat, if you don't repeat, right? You have to have two nodes or two vertices and one arc, right? But if you repeat, you have 2 and 2. So it has to do with kind of an odd, even something, okay? And go look it up for your homework. Okay? It's called 7 Bridges of Königsberg. This was the birth of the graph theory. Okay? So you have social phenomenon, you have modern phenomenon, network, connectivity, supply chain, energy flow, all kinds of stuff that's describable by a graph. Then you have the mathematics of graph theory. Then you have emergence properties, many of them. But the emergent property we want to know, we want to study is centrality. How come all of a sudden somebody became more important than the other person? It's not important in the sense that you like this person, but it's critical to the survival. So what is the natural response of analysts? Well, if this thing maps into a graph, and mathematicians have been studying graph for 300 years, why don't go to mathematics and see what they say about graph? Okay. So this was the birth of graph theoretic analysis of data. This is just, well, I'm actually quite proud of this because when I was in the Bank of Thailand, this was 2000 and the year was probably 2006, maybe 2008. Okay, this was long before Facebook was such a thing. It became a phenomenon it is today. It existed. It even had something like a precursor to Facebook. Was it? We forget. I think it was Space or High Five or something like that. The precursor of Facebook. Anyway, it was not the dominant social force of the day, and social network wasn't a thing. So I introduced the concept that banks. I was working for the central bank, right? So central bank at that time has to look after the health of the banking system. I'm a central bank. I'm looking after the bank system. Bank system consists of big banks, small banks, little banks, medium-sized banks. Yeah? If you don't look at it from the emergent property, who is the most important bank in Thailand? Which banks are important? You look at the big one, right? Right? You look at the big one. Okay? But I conceptualize connectivity between banks as graph. Banks are connected. You guys know that, right? You borrow money from bank. Stop talking about yourself. Yeah. You have relationship with banks. You know that. Okay? So this is banks. This is you, bunch of them. This is banks, this is you. But what you may not realize is that banks have relationships among them. Okay? In particular, banks borrow money from each other all the time. Okay? The money they borrow because they need to use money for something. It's basically a problem of liquidity balance. Okay? On a typical day, let's say you belong to a bank, 500 belong to a bank, right? Some of you may deposit, some of you may withdraw. Right? So it's not guaranteed that the amount of deposit and withdrawal is identical, right? It's not guaranteed. So on a typical day, maybe for this bank, you have more deposit than withdrawal. But let's say the sum of money in the whole system is the same. That means some other bank will have more withdrawal than deposit, right? It's not one-to-one, but overall it balances. So there is a natural overabundance of cash in one bank and depletion or deficit of cash in another bank. It's not because that bank is going out of business. No, this happens in that way. So what they have is, anybody know what it's called? Money market. Interbank money market. Interbank, between banks. So around 4 o'clock, SCB is going to assess its balance for the day. Okay? It's going to say, well, we need a little bit of cash because we have more withdrawal than deposit. Then we look around and we find which other bank have excess cash. Excess cash, right? Excess cash means bank that have more deposit than withdrawal. Okay? And I'll just borrow that. This was today. Because at the end of the day, I can't be short. Okay? And at the end of the day, people who have extra money not making money from it. So it's a win-win. One bank that has deficit in money needs money to make the account not negative. The other bank can have more money than it needs. That money is sitting there, it's not earning interest. So let it make money from the interest. So it's a win-win. Okay? This is called interbank money market. Okay? And it's been around forever. And the activities, happens very big and fast, let's say 4:30, maybe 3:30. Yeah? You settle the balance, and then everybody submits their results to the Bank of Thailand. The Bank of Thailand says, oh, good, everybody's okay. Yeah? If there's a bank that is so negative and nobody wants to live, that's the bank. Yeah? But normally the interbank happens every day. You don't even notice it. You don't even notice it. Yeah, it happens every single day. 3 o'clock, 4 o'clock. Now, you can imagine that this is what? This is a network, right? Banks are edges. The money flow. Sorry, banks are not edges. Banks are nodes. The money flow are edges. Banks are vertices. Money flows are arcs. Yeah, sometimes I get my words confused. Okay? Now, let's be more precise. Okay? Yeah. Arcs, edges, nodes, vertices. Okay? So you can actually go to now. These are very stylized graphs, very symmetric. Okay? My question for you is this: is the real life connection likely to be symmetric? Like, you connected to this person, or is it going to be rather random? Most of it's going to be rather random, right? Now, let's be more specific about my question. Let's say I have this. If these are the edges, sorry, the nodes, yeah, the vertex, yeah.
possible in M. What's possible? First of all, the first possibility is, yes, I is connected to J. Yeah, this is I, this is J, right? So node I is or isn't? No, it's not. Right? Simple, right? Simple, right? Either you know each other or you don't. Is that it? Well, think of it another way. Do you know your celebrity actor or actress? You know them, right? Do they know you? So the relationship is not necessarily symmetric, right? So you can have no connection. That's simple. Or you can have a connection, but that connection may require that you be specific. In other words, the edges have the beginning and end. That makes sense, right? So what is this? What is this? You know each other. You know each other is A knows B, B knows A. So in other words, we can say that sometimes you know both. Yeah? So it's easy to say, what do you mean to have no connection? Yeah? To have a connection, you have to be more specific. Is it a bidirectional connection? Right? Like if I tie string between you two, yeah, there's a connection. You go this way, she has to go, she goes this way, you have to go, right? But the connection can be one way because you are the boss. So you go this way, he follows, right? He goes this way, you don't care because you're not. He works for you. You don't work for him. So he has to follow you. You don't have to follow him. Same thing with Instagram, right? You can follow an actress or celebrities. They don't follow you. So it's not symmetric. It's bidirectional. In this case, the graph that has this kind of directionality is called direct connection graph. Yeah. So that's the first thing that you need to know. Is it directed? Directed means the arrow has a direction. There's an arrow. The arcs, the edges is an arrow. Now, so implicitly, if you have this connection like this, it's like two arrows going one way. Yeah? But quite like that. Now, let's be more specific. What do you mean by having a connection? Do you know your friend? Yes. Do you know him well? Ah. Do you know him well as much? Do you know him as much as he knows you? So there is what? A number associated with this friend. This can be termed a weight. Yeah? So instead of 0 for no, 1 for yes, it could be something like 0 for no, 0.5 for someone, 0.7 for a lot, right? Or it could be a connection of how people like each other. And if you like each other a lot, the connection is 0.9. But if you can like a person, you can also dislike a person. You can have minus 0.9. You really don't like them. Right? So this becomes weighted graph. Okay? The graph has some weight. Yeah. You have a graph. What do you start with? You start with nodes. Then you have edges, connecting nodes. That edge can be directed A to B is not the same thing as B to A, or it could be undirected. There's a connection, period. That connection can be Boolean, 0 or 1, yes or no, or it could be weighted with some number. In which case, I can say that A is more strongly connected to B than B is to C. You can do that, right? For example, in a network of friends, you can say, I'm closer to this guy than he is to the other person. Or if I'm going to count the line communication, you can say that these two have line connection, these two have line connection, but these two have 50 conversations a day. These two have 1 conversation a week. You can do that, right? And you can also make it positive and negative. This one have positive conversation, this two have negative conversation. Right? So all this is going to make things more complicated. Now, imagine how complicated the emergent communication is. Yeah? I look at it. You like each other 5%. You like each other 10%. You dislike each other minus 10%, something like that. What is the overall sentiment of the group? Okay? Who is the positive? Who's the feel-good factor of this vibe? Yeah? Who's the one that I can use to boost my efficiency of the efficiency of my marketing campaign? Okay. So, an example of the network phenomena that we are going to talk about today, for example, there's a game. I guess you guys don't know yet because you're a little bit too young. Okay, let's go to the second one. Social network. Who is the one that best spread gossip? Okay. Right now, let's assume that naturally you guys are all connected in a line connection. Yeah, not the formal one that I make you sign up. Yeah, just by virtue of being everybody is somehow connected. Yeah, maybe this person is not directly connected to that, but this person is connected to this. So nobody's left out. Nobody's left out. Now, I want to mobilize young people to do something, you know, to protest the quality of the food, canteen, or whatever political agenda I have. And I have 5,000 baht to take this person to who do I go for? Who do I go for? Right? Do I just randomly pick a student? No. You may be one person who just has one connection and nobody else. And if you say something, you're not going to pass on the information, right? So who is the central huojo? Thai word huojo, right? But huojo is a little bit obvious, like who's at the front. This one because it's more subtle. Yeah? Let me give you an example, extreme example. Let's say that everybody, right now, everybody's connected to the person next to them. Yeah? Now, let's use another example. Let's say that this block is all interconnected. Yeah? It's like a group. This one is like another group. But only this person and that from this group and that person from that group knows each other. Right? Then these two are going to be very important because their communication controls half the population. Right? Right? So you may, be able to just talk a lot to just one person, but it turns out that that one person is from another group. So it allows this transport of whatever information from this entire group that's well circulated to that group. Now, anybody can think of something else that's relevant to 2020? That's that effect. Coronavirus. Right? Coronavirus. Yeah? It's the guy who brings the disease from first from Wuhan to Thailand or to Europe to blah blah blah, right? We have this kind of virgin territory that the disease hasn't been to. Nobody is immune, right? One person arrives and boom. What else? So it's not just spreading gossips among friends, it's spreading virus. In other words, right now, when you listen to the news and they talk about contact tracing, and they say, who is the super spreader? They're looking for a graph centrality analysis. Okay? They have mathematicians working things like this out behind the scenes. Yeah? But you're not going to say the word like graph analysis on the news. But that's what is behind the scenes. That's what's behind the scenes. That's what data scientists working for World Health Organization does. Cities and airport. Yeah. If I want to make a transportation hub to make it here in Dallas or Memphis or blah blah blah, right? Bank account. Now, bank account, sometimes I want to identify unique players amongst individual account holder because that person may be running a money laundering scheme. Yeah. Financial institution, that's the one that I mentioned. That's the one that I mentioned to Thailand or to the Bank of Thailand, 2008. Yeah. Contagion risk. Contagion risk means when bank is short of money, he can't borrow because he borrows another bank might work. Everybody has it's called bank run, bank borrowing. Yeah. So contagion risk. Which one is the most systematic for? Now for the Bank of Thailand. Remember I told you guys that I don't really like this person in particular, but because he's a central node, I have to give him extra battery, right? Same thing. In the liquidity crisis for Thailand, Bank of Thailand would inject money to this bank, not because the two friends of central bank have business together, no, but because this bank is actually the one that is key to our liquidity flow. So this bank goes down, everybody goes down. So I would give extra battery to this guy so that the communication doesn't fail. The Bank of Thailand should give extra cash or protection overnight for this bank so the system doesn't fail. Okay? It's not a favor to that one person. Okay, it's a favor to the whole system. Okay, it's a favor to the whole system. Same thing, economy. Who has the most leverage? Now, by size alone, China, certainly. But what if certain countries like Thailand is a key bridge between, Southeast Asian bloc and East Asia, okay, or India, okay? We can be the connection, okay? That's why a lot of times, a lot of emerging economies make money from being the poor guy. Not because you're really important in any way, but the fact that you can put two and two together. Two is over here, two is over here. Nobody can put them together except these two. Okay? So it's that connectivity. So this is an example of network phenomenon. Okay? Now, the way it looks like this. You have the data, you have the graph, you have the matrix, you have the analysis. Now, what do I mean by that? Okay? The data is the field as collection of records that will be translated to who are your nodes? Who are your nodes? What is the strength of connection? Right? What's the strength of connection? Now, this is the flow of the data analysis, guys. But in terms of conceptualization, everything flows from the fact that it's a graph. Inherently, everything is a graph. Inherently, everything is a graph. Okay? The data describes the graph. Now, the matrix, how does the matrix enter? This is the next step. Because what? I want to know if Okay? There are three of you, A, B, and C. Right? A, B, and C. Okay? Is there a line connection between A and A? Well, this part is kind of like moon point, right? Is A connected to B? Let's say yes. Okay? If A is connected to B, B is also connected to A. Okay? Let's add B. And let's say you have something like this, and this. Okay? This is a matrix. What does it represent? A, B, C, and D. Well, A is connected to itself. Okay, A and B. Okay. B and C is connected. And then D and A is connected. Right? So there's a 1-to-1 between this. Now, if I wanted to make a directed graph, remember? Directed graph is not symmetric. Let's say A knows B and B doesn't know A. In this case, who knows who? Okay? Now, it doesn't have to be symmetric now, right? So I can do this. Say something like this. A knows B. A knows C also. And B also knows C. And D knows A. Okay? Now, just because it's directed, that doesn't mean that you can't have equals. You can have A knows B as well. They both know each other. Okay? See that? Right? Now, instead of having just one for yes, 0 for no, I can say how much, right? Then I can add numbers here, and I can add numbers here, here, right? So the graph is the concept of who is connected to whom, to what extent, in which direction. Yeah? Who, that's the nodes, are connected, that's the edges or the arcs, the vertices. In which direction? Directed, undirected, or both way, right? You can think of one-way street, right? From one city to this one, you have one corner to the next that's connected by one-way street. And you can say, is it a one-way? Is it a one-lane street? Big lane, 4-lane highway, right? So you can add some number. So the matrix and the graphs are exactly the same. Think graph, write matrix. And your data is going to be in the form of a matrix. Okay? The reason I write this pipeline this way is because sometimes people already know it's a graph, visualize, so they record this data as graph. Okay? But anyway, so these are basically the four things. The raw data itself, like the number, Tim knows Jane, Tim calls Jane 3 times a day, Jane calls Jack 50 times a day. Okay? Jack doesn't call anybody, something like that, right? That's your data, that's your reporting. You translate it into a matrix to store it as a data. Yeah, but exactly, matrix is the same thing as a graph. But the flow goes a little bit like this. Okay? Now, this is an example. Okay? Now, okay, let's pause a minute. You guys understand where we are so far, right? We're studying a mathematical object called graph. This graph can have many structures. It's symmetric and has numbers, right? What it's good for? Okay. Well, first of all, it's written as a matrix. Yeah, a graph in mathematics is written as a matrix, but it's a square matrix. Okay? A number of rows and number of columns is a number of nodes, the vertices, right? And the elements correspond to the arcs or the edges, negative, right? That's what we're doing. Okay? Now, we are going to walk through a number of examples and see how this is done in practice. Okay? Okay. First of all, this thing called adjacency matrix. Adjacency matrix, it just means the matrix of adjacency. What does adjacency mean? Guys, it's just a word, it's English word, it's not mathematics. Adjacency means you're next to one person, right? Are you two adjacent? Yes. Are you two adjacent? Yes. Are you two adjacent? No. Is adjacency a bi-directional relationship? And you be adjacent to her and her not to you? No. It's not like knowing your celebrity and celebrity doesn't know you. If you're next to him, he's next to you. So it's symmetric. Now, adjacency, is there like a quality to it? Like you are a lot more adjacent to, you know, most of the time, if you share a border, it's adjacent. So it's not described with a weighted matrix, right? It's not a weighted graph. Yeah? So it is a binary graph, right? 0 or 1. Binary matrix, 0 or 1. Symmetric. Okay? So if I ask you, what's an adjacency matrix? You tell me two things on exam. 1, what does it describe? 2, what is described? By the way, this is not what I expected when I asked you, you know, for homework or exam. What is it? What does it look like? So, what's an adjacency matrix? It's a matrix that describes which node is adjacent to which node, right? The connection is adjacency. And what does it look like? Well, you can say that it has to look symmetric. And it doesn't contain any funny number. Let's say 0 or 1. 0 or no. 1 or yes. Okay? Can be true, false, but yeah, 0 or 1. Okay. So, now, the data in this phase is interesting because before we get to the graph, the data doesn't come to a matrix form. It comes to a different form. Let me show you. Yeah. This is, by the way, this is a Python library, nx.readAdjustList. Okay, it's from this library called, where are we? Network X. Okay, Network X. The reason I did this is because this is actually a talk meant for Python Conference Thailand. Okay. So there it is. Okay. Yeah. So this is the data. The data looks like this. I have a list of Pranakon. The list has, you see, right? In other words, this is what the data. Stop talking about yourself, guys. Stop talking. The data gives you the list of who is your neighbor district. Who is connected to Pranakon? Who has neighbor? Who shares border with Pranakon? Do see. Okay. DataAnalytics. What about Dusit? Dusit has border with Panacon to one. Yeah, so it's not in a matrix form yet, right? It's just a data. Yeah, just a data. It's just a list. Yeah, just a list. We turn this into a matrix, and this is what the matrix looks like. Now, I told you that it is adjacency matrix. So number one, it's a matrix that reports which district is connected to which district, which has a border. Yeah? You have to say, what does it look like? What does it look like? What does this matrix look like? It has to be symmetric, because sharing border is a symmetric relationship. So does it look symmetric to you? Yes, it is symmetric. Yeah? And what value does it have? It can only contain two values, 0 and 1. Okay? Now, the diagonal is really not valid. It's there. Okay? The diagonal is there. Sometimes you would normalize it by putting all ones or all 0. Okay? Most of the time you put in all 0. So that is districts in Bangkok, right? The top left. You can see that where you live. There are, I think, 26 of them. Okay, so you can see, you can identify from distance visually the blue as the value 1. Yeah, if it's blue, then it is connected. So this is the data, right? And by the way, this is if you want to translate data. Remember, I told you there are 3 things, right? Data, graph, and matrix. Okay, this is the data, this is the graph, and this is the matrix, and that's the reality. Okay, so reality is that side, the matrix is this one, the data is here, and the graph is here. The data, you can't decide beforehand what form it comes. Okay? Now, if I look up this database, say from Bangkok Metropolitan Administration, and they give you the matrix, that'd be nice. But they don't give you the whole matrix, they give you the list. So we have to have an algorithm, a feeding algorithm that turns from the data in this form into matrix, adjacency matrix. And from then, the algorithm plots this. Okay? So you can see here, on cam, it's kind of like far out, right? Whereas something in the middle, like Bangkok, Dusit, Bangkok, is kind of somewhere in the middle. Okay? Now, this graph does not preserve geographical distance. Yeah, it's not saying that it's that close. It's not. It doesn't preserve. It just preserve the connectivity. So, degree centrality is very simple. The degree is like counting. How many neighbors we have? Okay, how many neighbors you have? And if you have more neighbors, you're more important. Okay, you're more important. Now, let me give you an extreme example of a funny looking city. Let's say you can kind of imagine that this district is kind of like important, it's kind of in the middle. This one is kind of in the outside, doesn't really matter. But if you just count the number of neighbors, it has the most. Right? So this would be the square measure of degree centrality. Doesn't give you the whole picture. Yeah? So degree centrality just say how many neighboring districts do you have? And who has the most neighbor district? The most is 7, I think. Yeah, the most is 7, right? And that's the job. The least is 2, I think. And that's Bang 9 is only neighbor with 2 more. Okay? So that's kind of like a simplest mathematical calculation. It's coming. Yeah. Again, even though it's simple, it already captures the emergent property of the centrality. Because now, all of a sudden, you say that it's a lot more important than Bang 9. Closeness, centrality. Closeness, centrality will be something like distance in number of districts. You have to go from one to the next. So in this case, you can say that Lucid is closest in the sense that it's kind of like to go from Lucid to say another district. You only need to jump 1 or 2 more districts. You don't need to go very far. It's kind of in the middle. Yeah. So it's sort of like the minimum number of connections. And this is not that interesting. This one is a lot more interesting. You know what this is? And the concept is like this. For any 2 districts to connect to each other, yeah? So you live in this district, you live in that district. You want to go through all other districts to get to the minimum the minimum number of districts, right? You do this for all the pair, for all the combination, for all the district to district travel. The one that has the greatest between the centrality is the one that occurs in most of the time. In other words, I enumerate all the minimum paths from district to district. And for each district, I count how many of those paths has to pass mine, has to pass me, has to be. So between this centrality is very interesting, right? So it doesn't matter where you want to go. Chances are you have to go through this. This is the concept of centrality. Now, as a data scientist, your job will be to select the right measure. Because it means different things. For logistics, it means one thing. Okay? This one is like a full path. These 2 districts is like full path because it doesn't matter who has to go to where, it has to pass through this. Now, in reality, this is but let's say that you have to go minimum distance mean minimum number of districts. Okay? Let's say every time you go to a district, you have to get 1. So you want to minimize number of districts by default. Okay? So this would be saying that people are trying to avoid going through many districts. They're trying to go through as many districts as they can. Still, you cannot avoid Lucid. So Lucid and Lucid and the job from a logistic viewpoint is the most important. It's the most critical. Again, if I have the battery, I have to give it to this guy because otherwise I'm going to fail. The battery has liquidity to take this back because it's key to the flow of interbank money market. If I'm the second priority of the transportation, I have to invest in the infrastructure of these 2 districts. Not because I like the people of that district more, but because it is central to the city. So this is the analysis. This is the whole class today is about analyzing the data that represents reality that is in the abstract form of connectivity. So in this case, I would invest a lot of money, not in something like Bang 9. Bang Na. Bang Na. Nobody goes to Bang Na unless you want to go to Bang Na. Okay? Bang Na is like off here. So for any pair of city, district to district, you never need to go to Bang Na first. Same with, say, San Mai, Ban, whatever. Okay? So those are on the outline. So there, there's one right there. It's not in between anything. Okay? You don't need to go there on the way. But certainly usage at that very important, very critical. Okay? For any pair of problems. Now, this one is called eigenvector centrality. I'll talk about it later because there's another chapter where this is a lot more. Yeah. So chances are, if I were working for a city planner or something like that, or company or something like that, the graph that I'm more likely to be interested in would probably be 3 minutes. Yeah. If I want to set some kind of thing, I'll probably put it somewhere in this thing. Okay. So those are different kind of centrality analysis, from bigger to small. But this is the one that I would get with. So there. Again, what's the data? List of district with its list of neighbor. What does it translate to? It translates to a density matrix. What does a density matrix look like? And you plot it as a graph. That. How do you analyze the emergent property? In this case, I'm only interested in one emergent property called centrality. But even that has many different definitions. The definition that I'm going to emphasize on for this problem is betweenness. Literally, you are more central because you are between everything. Okay? You have to go through this way. Now, this is how the code is done. D is equal to nx. Nx is the graph object. Okay? Nx dot read adjacency list. From the adjacency list function of metro only text encoding. This is some UTF-8. This is what TypeScript. You have to give it encoded. Okay? And as type name, yeah, we can create type name, district name, type English. That's like to plot because the algorithm uses English name. So to plot it, it's important to create a dictionary. So private fonts from English is N-R-A-N-A-N-O-N. This is N-U-S-I-I, right? And then I plot the figure, draw the network. Now, this is where the last thing is important. Sort it according to nx dot eigenvectors. In this case, it's eigenvector centrality. The previous example would be between the centrality of the graph, right? So this is it. This is how you would program in Lambda. Okay. Again, you will have to import this network X library from I'm really surprised, by the way, that this class hasn't picked up interest in doing project with this kind of connectivity, this network thing. Okay.